Our next major set of reactions that we're going to be talking about are going to be reactions that make double bonds. These are going to be broadly classified as elimination reactions. There are going to be two different types we're going to learn, much like how our nucleophilic substitution had both a unimolecular and a bimolecular, that is SN1 and SN2. We are going to have two different types of eliminations, a unimolecular and a bimolecular, which we're going to call E1 and E2. Now, there's a few other names which you could potentially call elimination reactions, and this is going to be based on the relative location of two different groups, our leaving group and a proton that's going to be deprotonated. So we can call this a 1-2 elimination or a beta elimination. We use Greek letters to count positions. Alpha is going to be right where the leaving group is, beta would be next, and then you could keep going down the Greek alphabet. Now, much like how in our SN1 and SN2 reactions, we had the exact same overall reaction, as in our starting materials and our final products could be predicted pretty easily. You can do that exact same thing with elimination. The main difference is going to be the actual mechanism. So back when we were talking about the idea of the impact of the nucleophile on our SN1 and SN2 reactions, I added a little caveat thinking about the difference between nucleophilicity and basicity. Nucleophilicity is kind of like the propensity or how good your structure is at attacking an electrophilic carbon. Basicity is how good you are at abstracting a proton. If you have a strong nucleophile, you're much more likely to do your substitution. If you have a strong base, you're much more likely to eliminate. In elimination reactions, we are going to have a base, which you can call like B, and B and our nucleophile are both very similar. They're going to be structures that are going to oftentimes be charged. They're often going to have, or they're always going to have a lone pair for our sake. And one of the big differentiations that we need to do is, if we look at a structure, is that more nucleophilic or basic? And that's going to be something that we'll get to in a later video. But we're going to have a base, and that base is going to interact with our substrate. Our substrate is still going to have a leaving group. So you have, like, for example, G for your leaving group. And you're also then going to have, let me do a different color here, a proton. And the key thing is your proton needs to be exactly one carbon away from your leaving group. This is where we get that 1-2 or that beta relationship. So on the carbon that is connected to your leaving group, one carbon away, you have a hydrogen. And what's going to happen is that hydrogen is going to be abstracted as a proton to your base, and that's going to form your conjugate acid. Your leaving group is going to leave, and then you're going to then get a double bond at the location between your hydrogen and your leaving group. Now, leaving groups, you should have a pretty good grasp for. We talked about the different types of leaving groups when we were talking about SN1 and SN2. We talked about typically halogens. You see a lot of like bromines or chlorines, iodides. Alcohols are not good leaving groups, but you can turn it into like an oxonium, or you could turn it into like a mesylate or a tosylate. Those would all be kind of examples of like what leaving group you would see. One struggle is there are a lot of different hydrogens that can exist on a molecule. And one of the questions is, how do you know which hydrogen you're going to abstract? And to figure that out, or to kind of get like a rule or kind of a thought process, or maybe a rule of thumb is probably good, we are going to start by introducing this idea of Zaitsev's rule. This idea of Zaitsev's rule is kind of built on this general idea of regiochemistry. And regiochemistry is going to describe between two different isomers, which of those is going to be more favored. And in the homework for chapter 6, there was actually the very last product. There was two different, I think it was chapter 4 actually. For chapter 4 with your radicals. In the last question of your radical homework, there was two different products for the bromination. And there was a choice of B and a choice of D, and we're talking about which of those is more stable. And at that point, you could have said either, because you haven't learned Zaitsev's rule. at this point, we'll now actually understand why D is actually more stable than what B was in that final homework question for chapter 4. So Zaitsev's rule is going to generally fall into this general category of we want to make the most substituted double bond. So in a case where you have multiple different hydrogens, which you could abstract, you are going to make a double bond that is going to be surrounded by the largest amount of things. So here, there's actually an example of an elimination that's going to occur. We have a leaving group of a chlorine, and then there is a hydrogen that is not drawn in but exists one away, as well as down here, one away. Each of those can be eliminated, and depending on if you eliminate the first one to get, well, I guess the lower one would get you the second product. The higher one would get you the first product. Each of those can form, but one of those is going to be a major product. And when we think about which is going to be favored, the more substituted or the one that has the most carbon stuff around that double bond. So if you look at this first product here, I would have 1, 2, 3, which we would call tri-substituted double bond, where in this one I have 1, 2, and we would call this di-substituted. If you're able to add more stuff or more substitution around the double bond, that will help stabilize it. So in here, your major elimination product is going to be the first, and your minor product will be the second, based on this idea of Zaitsev's rule. Now, we will spend a lot more time in a future video talking about predicting products and showing mechanisms and all of that sort. But I just wanted to start a little bit about the stability of a double bond. Now, you can see all kinds of different examples here in terms of like the stability of alkenes. Here, all of them are going to be a simple double bond with either R, which is going to be a carbon stuff, or a hydrogen. Our most stable structure is going to be this very last one on the farthest to the right, where you have 4 different things. That is a tetra-substituted. If you have all just hydrogens, then it's just simply an ethane. Or if you had a mono-substituted, those are going to be the lowest. If you, for example, have 2, there is a bunch of different conformations which those can have. We practice on naming with the E or Z. An example of this first one here, this would be the same side, which would be Z. This one would be E, and then this one is actually going to be achiral. All 3 of those examples, your E conformer, your Z conformer, or your achiral molecule, all of those are di-substituted, and those are all going to have roughly the exact same energy because you have exactly 2 things around it. Now, we can kind of do a little bit of prediction here of Zaitsev's rule. So I have an example above. We have a 1, 2, 3, 4 carbon system with a bromine, and we are going to react this with a base. This is an ethoxide base in the presence of ethanol, which is going to be our solvent. When we are going to think about an elimination reaction, one of the very first things that we're going to think about is what is our leaving group. And here I see that I have a bromine. That's going to be my leaving group. Once I identify my leaving group, I'm going to look 1 carbon to the left or the right or top or bottom, 1 carbon away, and look for hydrogens. And here I have a hydrogen at this position, which I'll call HA, and then a hydrogen over here, which I can call HB. Actually, I'll go ahead and do that in a different color. We'll do a red and a blue. Maybe make this into a green for our leaving group. So depending on if I abstract HA or HB, I will get 2 different products. If I subtract HA, I'm going to get a double bond between HA and my leaving group, my bromine. So if I draw that base backbone, my double bond would be right there, in between where my HA was and my bromine. If I abstract HB, I would have that same general structure, but my double bond that I'm going to abstract is going to be on the, or where I'm going to form my double bond is going to be based on the carbon between where my proton was abstracted in my leaving group, which would be all the way out here. Of these 2 different products, I would have my very first one which is a di-substituted double bond. I have 2 different carbon stuff on the left and the right side of the double bond. On the other one, the blue one, I only have 1 carbon stuff, and the other 3 spots are going to be hydrogens. So we're going to describe our major product, or our most stable, based on Zaitsev's rule, being the structure in red, abstracting HA. The abstraction of HB is going to give us a minor product. So if you were asked just to predict the major product, you would only show the one in red by abstracting the HA. And that's kind of a general background on the idea of Zaitsev's rule. In our next video, we're going to spend a bunch of time talking and thinking about the actual mechanism and how this forms, but I wanted to give a little bit of background on how I randomly choose which hydrogen to abstract before we get into that. So that will wrap up the broad strokes on Zaitsev's rule, and I'll see you in the next one when we start talking about unimolecular elimination.